Okay, we are live. And I'll also record in the cloud. Okay, we are live and the recording started as well.
Sure.
So welcome to the IEEE Computer Society Silicon Valley chapter event. Today's event is on mobile heterogeneous computing. A brief introduction to our chapter. Our chapter is the largest chapter in the Silicon Valley section of IEEE, with over 4,000 subscribers in our mailing list and a strong following of over 12,300 on Twitter alone. We are uniquely positioned by virtue of our location and available expertise, and thanks to the COVID syndrome pandemic, we are able to leverage excellent speakers, distinguished speakers from all over the world. And today we have with us Dr. Tulika Mitra. She is the Provost Chair Professor of Computer Science and Vice Provost for Academic Affairs at National University of Singapore. It's 9 a.m. in Singapore right now. So she will be talking on mobile heterogeneous computing. So mobile heterogeneous computing in the form of multiprocessor system on chips composed of various processing elements such as general purpose cores with differing characteristics, GPUs, DSPs, non-programmable accelerators, and reconfigurable computing are expected to dominate the current and the future mobile platform landscape. The heterogeneity enables a computational kernel with specific requirements to be paired with the processing elements ideally suited to perform that computation, leading to substantially improved performance and energy efficiency. While heterogeneous computing is an attractive proposition in theory, considerable software support at all levels is essential to fully realize its promises. The system software needs to orchestrate the different on-chip compute resources in a synergistic manner with minimal engagement from the application developers. The current state of the art is inadequate in the software dimension, despite tremendous progress and success in designing heterogeneous MPSoCs for mobile devices. This talk will put the spotlight on the software perspective of mobile heterogeneous computing, especially in the context of popular emerging applications such as 3D gaming, multimedia processing, and analytics. The talk will introduce the technology trends driving the mobile heterogeneous computing revolution, provide an overview of computationally and performance divergent compute elements, and present efforts at compiler and runtime management layers to unleash its potential towards high performance, energy efficient computing. So to introduce Dr. Tulika Mitra. Dr. Mitra is Provost Chair Professor of Computer Science and Vice Provost Academic Affairs at National University of Singapore. Her research interests span various aspects of design automation of embedded real-time systems, cyber physical systems, and Internet of Things, with particular emphasis on low-power computing, heterogeneous computing, application-specific processors, and software timing analysis optimizations. She has authored over 150 scientific publications in leading international journals and conferences and holds multiple US patents. Her research has been recognized by Best Paper Awards and nominations in leading conferences. Professor Mitra currently serves as the editor-in-chief of the ACM Transactions on Embedded Computing and associate editor of IEEE Design and Test and IEEE Micro. She has served as Deputy Editor-in-Chief of IEEE Embedded Systems Letters and Associate Editor of IEEE Transactions on Computer-Aided Design of Integrated Circuits and Systems in the past. She has served in the organizing and program committees of several major conferences in embedded systems, real-time systems, and electronic design automation, including General Chair of Embedded Systems. She was also the program chair of IC-CAD 2021, EMOS SFT 2014, CASES 2018. She has been a member of the ACM Publications Board, co-chairing the New Publications Committee for the years 2018 and 2020. So before I hand it over to Professor Mitra, I just wanted to mention that the links to the video and the slides will be posted on our website in about a week. And the video will also be made available on IEEE.tv. The event itself is being live telecasted, so it will also be available on YouTube channel. And if anyone has questions, please post them on the chat window, and I can relay them over to Professor Mitra. So with that, we are really very glad to have you, Professor Mitra, and it's all over to you. I will stop sharing so that you can share your slides.
Thank you, Vishnu. Thanks for inviting me, and it's a real pleasure to be able to connect with you all virtually. So as Vishnu mentioned, I'm going to talk about sort of the software perspective of mobile heterogeneous computing. But before I do that, let me kind of introduce what I mean by mobile heterogeneous computing a little bit. In some sense, I think of mobile and embedded heterogeneous computing as kind of the canary in the coal mine. In the sense that all the issues that we have faced in this aspect and all the work that we have done in this domain, it seems like it's going to be equally applicable to the server space and high performance computing space moving forward, as all these trends are now kind of coming to that high performance computing space as well. And I'm going to talk briefly about that at the end of my talk. But first, to just kind of explain the context. Mobile heterogeneous computing is nothing but a system on chip that consists of many different kinds of computing elements, including CPU cores, GPU cores, DSPs, and accelerators. And you can see over here, for example, I just took Apple A12, but Apple A15, which is the most recent one, does not look very different either. What you can see is that it has kind of, two big CPU cores. It has 4 small CPU cores over here, a bunch of GPU cores together that forms the GPU for this system. It has a neural processing unit, and there are a bunch of other IPs that does video processing, audio processing, and so on and so forth. So this is a very, very heterogeneous system. It does not look simply like just CPU processing cores. So why is that happening? Of course, it's happening because at least so far, we have been very fortunate to ride the wave of Moore's law, which essentially means that the number of transistors that you can put in the same area is doubling every year or two. And if you just look at the numbers, they're kind of staggering. I think the Apple chip that's coming to your MacBook Pro that was just recently announced has 57 billion transistors on that chip at a 5 nanometer TSMC technology. And if we look at just Apple A15, for example, or even Huawei Kirin chip that's coming on your mobile phones, has about 15 billion of these transistors. So these chips are really complex, really huge, has large number of transistors riding the wave of Moore's law. However, there is a sort of a difficulty that we are facing in this aspect starting from 2004, and that's because Moore's law went hand in hand with Dennard scaling. And what is Dennard scaling? Dennard scaling essentially says that as you scale down the transistors transistors, to put more transistors on a chip, the power density remains constant. That means that the power was not going up, even though you were increasing the number of transistors. And that was great, because then you can put in more functionality, you can put in more transistors, and your power consumption still remains exactly the same as before. However, that's not happening anymore. And that's why what's happening is that we cannot increase the processor frequencies, and instead we are going for multi-core and many-core solutions, where you put many cores on the system and keep the frequency constant, or even the frequency is going lower. Unfortunately, again, we hit a roadblock in terms of putting many cores and many processors on a single chip, and that's because of this concept, what is known as the concept of dark silicon. So what is this? So essentially what happens is that you can put a lot of functionality, a lot of transistors on the chip, and you can put a lot of cores on chip, but you will not be able to switch on all of them at the same time. And the reason you cannot do that is because you're going to hit the thermal design power constraints, right? So let's suppose for my mobile phone, it's about 2 watts. So if you go actually beyond 2 watts, then everything will actually kind of shut down. But if you switch on everything on your phone, it can easily go all the way up to 10 watts, for example. So basically, you cannot use the entire chip area, and you can, and so most of your chip at runtime will be dark. And at 5 nanometer, 80% of the chip is expected to be dark, which means you can only effectively use 20% of the chip area. So how can you solve this problem? Now, one thing you can say is that I'm not going to have these big chips, I'm going to just have the small chips, but that's kind of, just saying that, okay, I accept defeat, and that's not something that we are used to doing. So instead, what the architects and the circuit designers and all have done is that they have turned this problem into an opportunity. So what is this opportunity? The opportunity is that silicon area is very cheap because of Moore's law. That has, that was true for till today. So the silicon area is very cheap, but the power is very, very costly, right? So we cannot afford to have a lot of things switched on at the same time, because we are limited by power. But we can put a lot of things on the chip. So instead of just having the same core repeated again and again and putting the 60 of them on chip, what made sense in the context of mobile and embedded systems is to have different kinds of cores on the same chip. And these different cores, so these heterogeneous cores, support very different functionality. As you can see, the CPU, the GPU, the NPU, they are actually supporting very different functionality. So depending on what application you are running, you can switch on the most appropriate core, you can switch off the rest of the chip, and you can get very efficient execution, you can get very high performance execution. So that's kind of the motive behind this heterogeneous mobile heterogeneous computing system. And the reason that it happened in the mobile system first is because the thermal design power limit is very true for these systems, and it was not so much of a problem in your desktop and the server platforms, where you can actually do active cooling, which is not possible in these systems. But as we will see that, this heterogeneous computing is also coming to that space as well. It's just that it's coming a little later. So if I look at the heterogeneity, we can broadly classify this heterogeneity into 2 classes. The first one is functional heterogeneity. By functional heterogeneity, what I mean is that you have very different kinds of processing element. For example, DSPs, GPUs, FPGAs, and coarse grained reconfigurable array, which I'm going to talk about a little bit. As well as non-programmable accelerators, for example, NPU or Google's TPU is a very good example of video encoders. And you can see those here. For example, this is the Qualcomm chip, Qualcomm Snapdragon chip that's there in a lot of these mobile processors, which has many different kinds of processing elements. Similarly, this is from NVIDIA, which is the Tegra processor. You can see audio, video, and so on. Okay, so that's one part. The other part is kind of functional heterogeneity, where all the cores have the same instruction set architecture. So you can take the same same software and run the software on these cores, but they are very different in terms of power performance characteristics. And here is again one example from Qualcomm Snapdragon in the form of ARM big dot little architectures, where you have the performance cores you can see over here, which is far more complex, very complex pipeline running at higher frequency, has more caches and so on. And so it offers very high performance, but at the same time, it's also very low power. And on the other hand, you have the little cores. These little cores are actually very, very efficient. They have, you can see the pipeline is much more simple, running at lower frequency, has lower, memory requirement and so on and so forth. But at the same time, the performance is actually not going to be that great, right? So this is kind of performance oriented and this is kind of efficiency oriented, and you put these two in the same chip, and depending on what application you are running. So for example, if you're in your mobile phone, you are just looking at your emails, which is what I do most of the time, then you are able to run it on this efficient core. But at the same time, if you are doing a very intensive gaming application, or you are running the websites with Flash, in that case you need to go to the performance core, right? So you kind of try to get the best out of both the worlds. So I hope I have convinced you that these systems right now are actually a very big engineering feat. They are really complex, yet they work and they are really great. Unfortunately, the hardware is only part of the equations. Without the software, the soul of the system is missing, and you cannot do anything about it. So what I'm going to focus on is that how do you actually develop software for these heterogeneous computing systems? And in some sense, it's kind of the best of times, but it's also worst of times, because we have made this tremendous progress with heterogeneous computing, but the software development remains as challenging, if not more challenging. We were already struggling in designing parallel software for homogeneous computing systems, and now you throw in this heterogeneous computing systems. There are a number of other questions that you need to answer. First is that given an application, which one should I choose? I have so many choices. Which core or accelerator should I go for? And sometimes it might be that you should not kind of execute it on just one type of core, but maybe you get the best performance and power efficiency if you can orchestrate the execution across multiple cores or accelerators. But then how, as a software developer, do I go about doing it? And finally, the whole thing started because of these thermal power design constraints, and also in the mobile context, what is very important is the battery life, right? That's the single most important concern for any mobile phone user. So, how do you reconcile this? And in this context, this is not so much for the software developer, but more for the operating system side. How do you handle these constraints? So I'm going to briefly kind of go through each of these points and give a little bit of an overview. So I'm not going to go into the details, but I'm happy to answer any questions. So let's first look at kind of the compute core selection, right? And I'm going to choose the three broad categories of compute elements that you can see in today's mobile phones, as well as embedded systems. The first one is, of course, the CPU, and where sort of ARM is more like the dominating instruction set architecture. You can have the GPU cores, and you can have, of course, the FPGAs. Now let's look at kind of a code. You probably have it in C or C++. Now looking at this code, how do you know that how well it is going to perform on a CPU? That's very easy. You compile that and you get the performance, and the compilers are typically very, very optimized, well optimized, right? Now, if you want to get that performance on a GPU, however, you need to actually transform it into CUDA or OpenCL and run it on the GPU to get the performance. And it's not very easy for you to do that, because you can probably create a fast cut. For those of you who have programmed, you know that it's very easy to create a fast cut CUDA or OpenCL code that might be functionally correct, but in order to get the performance out of it, it's really, really a difficult proposition, right? So if I just kind of create a fast cut, first of all, I need to do this transformation, and I need to get the execution time, which is kind of a difficult proposition in the first place, right? And for FPGA, it's even more complex because again, we have made tremendous progress in high-level synthesis, where we can take applications in C or C++, and we can automatically generate the RTL code. However, that RTL code again is, first of all, you still need a little bit of domain knowledge in order to be able to do that. And again, getting the performance out of it is extremely difficult because you need to put a lot of pragmas out there in order to decide exactly how this system should be synthesized. So the bottom line is that given a sequential piece of code, be it C, C++, or Python, it's extremely challenging for us to figure out what exactly is the performance going to be on the different systems and choose it, right? So what we want to do is that minimize that effort and give you a hint that, okay, you know what exactly is going to be the performance of the different accelerators, so that you can just choose it without going through this burden of really sort of transforming the code and then compiling it and then getting the performance and optimizing it. So my group has developed two of these performance prediction models, one for FPGAs and one for GPU. But more importantly, apart from providing the performance prediction model, what these tools do is that they provide performance insights to the software developers. So for example, we can say that, for this GPU, this should be the block size such that you can get the maximum performance out of the system. And we'll see that that's a very powerful tool to have as a software developer. So how do you go about doing it, right? Let's look at the FPGAs, right? Currently, the way the high-level synthesis happens is that you provide a number of pragmas to the high-level synthesis tool. So for example, you say that loop unrolling should be, this should be the loop unrolling factor, this should be the array partitioning factors, this should be the loop pipelining, or there might not be loop pipelining, and so on. This should be the tile size. So there is a lot of choices that you have to get in order to get performance out of these systems. So with high-level synthesis, for each of these design points or each of these choices, we need to actually synthesize the code, and that synthesis can take sometimes days, simply because this is very, very difficult. It's much more difficult than just the normal compilation, right? So if I want to choose the optimal pragmas, then I have to do this synthesis for thousands of points and then choose the optimal one, and it's going to just take days to do that. Now, what is our insight? What we want to do is that we want to give you a performance estimate, but the advantage that we take care of is that we simply kind of point you to the best pragma that you can use in order to get the best performance, but we do not synthesize the code directly. So once we have given you that this is the best pragma for this particular application, you can go through the high-level synthesis process just once. Instead of for 1,000 points, you can just go through it once, and you can get the best code and you can get the best performance out of it. So we do that through a program analysis technique, where we take the code, we get the LLVM intermediate representation, we give this code set of representative inputs, kind of like for profiling, we create dynamic traces out of it, and then we create a dynamic data flow graph instead of a static data flow graph. The advantage is that we don't need to worry about aliasing and things like that, which actually makes things very complicated for the real high-level synthesis. And so with that, we do an abstract high-level synthesis, and we get the performance out of these systems. And it's pretty good. So you can see the accuracy for different benchmarks compared to the best performing sort of pragmas that has been really gone through the high-level synthesis tools compared to our very high-level estimation. And you can see that the accuracy is very, very good. But at the same time, what is more important is that the average time to explore this, all these possibilities went down from 28 hours on an average using high-level synthesis tools to just 1.6 minutes. So this gives you a very powerful tool for you to explore. And what was interesting is that sometimes we figured out that that in certain cases, the high-level synthesis tool was giving a very different result. And then we realized that that's because it could not figure out that there are certain optimizations that we could do, and our tool can actually suggest these optimizations to the high-level synthesis tool in order to make it work better. And then we kind of try to apply the same context for the GPU. Now, remember that in case of GPU, what is important is that we should be able to parallelize the code, and we should be able to have the memory managed appropriately, because the DPU has many different memory hierarchies, and where you keep your data is very, very important. So again, we kind of apply a similar notion of creating the dynamic traces. From that, we automatically form. So remember, we start actually with a sequential piece of code. We automatically form the warps. We automatically form the blocks from there. And we have a very sort of comprehensive analysis that we do a modeling of the memory behavior, we do a modeling of the computation, and we actually predict the execution time. And again, you can see across a large number of benchmarks applications. These are important for mobile and heterogeneous systems. The estimation error on an average is about 9%, and it's as low as 2.66%, which is actually, for me, it was quite amazing, simply because we are not even doing any parallelization. It's completely being done automatically. So coming back to the problem that we were trying to solve, so given an application, and then what we want to tell the software developer is that, should we go for a GPU, should we go for an FPGA, or should we go for a CPU, right? And here you can see that this is the estimated time, and these are the actual times, which are pretty close, and it actually gives us a very sort of confident answer. So with our tool, just using few minutes, you can tell that, okay, this particular application, you should send it to a GPU, or this particular application, you should send it to an FPGA. So that's kind of, if you want to make a choice, but sometimes maybe you do not want to make a choice. Instead, you want to use all the compute elements that are available on chip if possible. And, that's kind of, you can achieve that using OpenCL, for example, which is a free open standard for cross-platform parallel programming on different computing elements, including CPU, GPUs, and FPGAs. Here is an example where you are actually running image processing on a mobile phone using OpenCL. Now, with OpenCL, what you can do, interestingly, is that you can, so this is the workload that you have, and you can partition it across heterogeneous compute elements. In this case, for example, across the CPU and the GPU. Here I have the ARM big dot little architecture that I talked about earlier, and I have a ARM Mali GPU, and I'm trying to decide what part of the code should go to the little code, big code, as well as the GPU. And again, this is a very complex design space exploration problem, but if you can do it properly, you can have rich dividends. So you can see here, for example, I'm showing you these results for two different applications of our design space exploration. On the x-axis is the execution time, on the y-axis is the energy consumption for that application, and lower is better. So, you should be at this end. So this is the Pareto curve that we are looking at. Now, interestingly, as you can see, this is a GPU bound application. So what we are trying to decide is that, how should I partition the workload across these different heterogeneous elements? And we also take into account the dynamic voltage and frequency scaling in order to reduce the energy consumption and the memory contention across all these devices that are all trying to go to the memory. Now, for this particular application, which is a 2D convolution, it is actually a GPU bound application. So what you can see is that the best performance energy trade-off you get by using, so A15 is a big core, A7 is a small core, and the GPU. So you get the best kind of trade-off by using all the elements together. However, because this is a GPU bound, the rest of the points that you are seeing here, these blue dots and the green things, they are actually all sort of ARM cores with GPU, because that's the one that gives you the best kind of results. On the other hand, if you look over here, this is sort of the SYR2K, which is a CPU bound application. And you can see again, even though using all of the cores gives you the best kind of performance energy point, the ones that are closer to it, so these ones, for example, these do not have the GPU. This is just the small and the big core, and the reason again being that this is a CPU bound application. So again, so what we do here is that we develop a lot of models that can easily get you the best point that you need to use in order to partition this workload across the different cores, and also do the dynamic voltage frequency scaling, and we get about average about 20% runtime improvement compared to running it on a single type of core, right? And then the other issue that comes in as soon as you try to kind of run this across multiple cores is that we get hit by this thermal design limit that we talked about earlier, and the reason that why we had heterogeneous computing in the first place. And with the thermal design limit, there are some interesting kind of effects that comes into play. So for example, over here, the CPU can be run at different frequency levels from 2 gigahertz to 900 megahertz. Now, one would imagine that, you know, I should run it at the highest frequency, 2 gigahertz, to get the best performance. However, that's not the case because the thermal throttling kind of kicks in at 2 gigahertz. So you can see over here with different CPU workload partition, and we are looking at the execution time, and the lower is better. What you see is that I get the best execution time by using 1.5 gigahertz frequency as opposed to 2 gigahertz frequency, which is kind of somewhere out here. So it has more longer execution time, and that's because of the thermal throttling. So again, you know, you need to kind of take into account all of these factors, and the models again come in very handy here. So you need to kind of look at the profile of the application, look at the CPU profile, look at the GPU profile, decide on how the workload partition is going to be, how it is going to lead to thermal throttling, and you want to minimize that thermal throttling by choosing the frequencies that will not lead to throttling and that will not lead to too much memory contention. So you want to kind of choose that best execution platform. So, you know, so basically what you need to do is for these kind of applications, if you want the development to be transparent to the software developer as much as possible, they just give you the reference code and you should be able to kind of run it seamlessly onto these kind of platforms. Then you need support from this kind of modeling tools in order to give you the power to make informed choices. And now let's kind of look at how this kind of heterogeneous computing, do they kind of work well with a very important workload on mobile platforms today, which is the deep learning workloads. So can we kind of apply the same concepts in these kind of systems? And we'll show that with this Kirin platform, which has big.little CPU, it has the GPU, it has the neural processing unit, which are the 4 things that I'm going to use in order to run the machine learning workload, right? So here we actually kind of look at the throughput as well as the power for running sort of convolution neural network workloads, AlexNet to SqueezeNet onto these systems. And what you can see, these 3 bars on the left are actually from Exynos system, which is Samsung Exynos mobile chips, which are kind of the earlier version of mobile systems. And these 3 are coming from these 4, sorry, are coming from the Huawei Kirin chip, which is kind of the more recent mobile SoC platform. And you know, there is no surprise that what you see is that, of course, Kirin is performing better because it's a newer generation of mobile SoC. But if you look inside, this is kind of this is the small core. This is the big CPU core, this is the GPU, and this is the NPU. Again, as you can see, as we go up there, the GPU power is much more compared to the CPU, GPU performance is more, but it is not as kind of different as you would expect in a desktop GPU. And the reason being is that these GPUs are not as powerful in the mobile systems. So they are actually somewhat similar performance, maybe twice, 2.5x compared to the CPU cluster. But the high-end GPUs actually consume a whole lot of power. So you can see that their power consumption can be quite big. The NPUs are actually doing very good in terms of the power. In terms of the performance, they're not that different from the GPU either, again, because these NPUs are not as powerful, but they are actually very, very efficient. But the takeaway message from this is that low-end SoCs have no single component that can sustain the ML workloads. Unfortunately, okay, yeah, so this is the energy efficiency, and here really the NPU scores, because you can see that its energy efficiency is much better than any of the systems that you have. And interestingly, the energy efficiency of the GPU is worse than the energy efficiency of the big CPU core. Now, if you look at the mobile platforms, of course, some of us are very fortunate to have these powerful next generation mobile platforms, but a lot of people in the world are using the simple devices that are kind of closer to this side rather than this side. And a common denominator across all these devices are the ARM big and little clusters and maybe a less powerful GPU. So what we wanted to see is that can we actually run this ML workloads using all the codes that are available on the system and get the best performance out of it. And as you can see over here, this is where we are actually running it across all the systems. We are using all the cores on the chip to run that, and this is the result where we are co-executing using all the systems, including the NPU, and you can see that we can get almost 2x performance improvement or throughput improvement compared to running it on one of the systems, just one of the systems. And here is another attempt for us to do this using only the big dot little part of the code and kind of ignoring all the NPUs and things like that. And the reason again being that that's kind of the common denominator that is present in all the mobile platforms. All the mobile platforms may not have the fancy GPU or the NPU. Now, what is interesting here is that we actually kind of converted the convolutional neural network execution on these platforms to a pipelined execution, where we were actually mapping part of the layers of the neural network onto the different cores. And this was a lot of engineering challenge here involved here. Apart from the fact that we had to kind of course, do again a design space exploration and figure out what is the best choice. But what we ended up having is a very interesting result. So what you see here is multiple different implementation. This is the implementation from the ARM sort of manually developed sort of library for this execution of the CNN. This is from TVM, and these two are our implementations that are using this pipeline execution. And this is TensorFlow Lite. So what is kind of interesting is that we actually managed to get higher throughput. Even though these codes are highly optimized, we can still kind of get higher throughput. This one is using quantization. By the way, all of these are also using quantization, but this one is using quantization and compared to this one, which is not using quantization. And as you can see, that we can go all the way up to 30 images per second simply by using the ARM processors and not using any NPU or GPU, and so on. So, that kind of gives a sense of how powerful the heterogeneous computing can be. Here is another example where we actually use the GPU. We use the Neon, which is the DSP sort of component that we have with the ARM CPU, and this is on a Xilinx Zinc FPGA. And again, we take a neural network and we kind of distribute the workload across all the different clusters. And you can see that this is just using the ARM with Neon. This is using just the FPGA, and this is using both, and we can get significant sort of performance improvement as well as lower power by using something like that. Okay, so that kind of brings me to the next part, which I will go through very, very briefly, is that once you kind of try to use all those systems together, and we saw it again earlier, that if you try to do that, then you might actually hit the thermal design limit, and at that point, your system will shut down simply to kind of not risk getting damaged, right? And this kind of dark silicon problem is very real. This is a cheap Samsung Exynos 7420 that we used back in kind of, I think, 2017-18. And if you look at the power of the different components, this is the big cores, about 5 watts, small core about 1 watt, and the GPU about 5 watt. So together, if you run all of them at the highest frequency points, you get about 10.45 watts. So what you really need to do is kind of, really remain within that design, thermal design power, but at the same time, you really need to be able to provide the performance that you need. So what you need to be able to do is that map the tasks to the appropriate core and migrate if necessary, as well as you need to kind of do dynamic voltage frequency scaling for each of the cores or clusters, depending on what application is running. Now, what is interesting is that for mobile platforms, we are running interactive application. So for us, the quality of service is the key metric, right? So if you need to do 30 frames per second, then if you provide 45 frames per second, you are just wasting energy without providing any sort of useful performance or user experience. So what we want is to kind of try to take advantage of that. We just want to provide the QoS that is required. We don't want to go beyond that, and we want to save energy that way. So one of the key problems that we faced here is it is difficult to sort of do the dynamic voltage frequency scaling in the operating system, because in this kind of heterogeneous system, for example, you have a Linux governor that is doing the power management for the CPU, and you have a GPU dynamic voltage frequency scaling, which is kind of a firmware-based governor, and they typically do not kind of act in synchrony. So sometimes they can actually be doing things cross-purpose, which kind of makes the problem very, very challenging. So I'm not going to go through these, but essentially what you need to do is have a cooperative power management feature and the thermal management feature, where you need to look at what's going on in the CPU, we need to look at what's going on in the GPU, and kind of make a decision that is best for the application as a whole. And this is for 3D gaming applications, which are sort of the most intensive workload on a mobile platform. As you can see, when the CPU is running very intensive, maybe it is creating the scene, the GPU is kind of sitting idle, and when the GPU is doing a lot of work like rendering the scene, the CPU is sitting idle. So it is important for us to have a sense of that application and what is the requirement of that application, and send those hooks or hints to the operating system so that you can actually do a much better job. And the same thing happened with the thermal behavior. You can see when the CPU is doing stuff, it's very, very hot, and then the GPU becomes hot, and then you kind of toggle between the two. And again, with the coordinated thermal management, you can bring down not only the peak temperature. So for example, compared to Linux, we were able to bring down the temperature from 83 degrees centigrade to 77 degrees centigrade. We improved the frames per second because the thermal throttling was not happening, and we actually reduced the temperature variation significantly. And again, the temperature variation is very, very important to control so that you do not have the damage to the chip. Uh, and finally, you also need to be able to do the migration of the tasks from the simple code to the big code, or from the big code to the small code as and when necessary. As you can see, so for this particular application, for example, this is the range in which you should be in terms of the performance or quality of service. If you fall below that range, then you should move to the big code. And if you are above that range, you should move to the small code. And you can see that, in this particular case, this is sort of the one that we are doing in terms of going between the two, whereas this green one is just running on the small code, and this one is just running on the big code. So one is giving you very high performance, the other one is giving you very low energy, but none of them are meeting the QoS constraints, as well as providing very good energy. And we can do that by using this kind of migrations. And again, there is a lot of theory that you need to develop in order to be able to provide optimal performance. And some of these techniques have actually been now used in Linaro in order to get the best performance power behavior from these chips. So as I mentioned at the beginning of my talk, is that, we have faced all these issues in embedded systems for a long time, but now these things are coming to your server systems and high performance computing systems as well. Intel just announced the Intel Adler Lake hybrid CPU. I think it's coming very soon. And it's the first time that Intel is actually going for this kind of a hybrid big dot little kind of architecture. So you can see they have a performance core, and then they have an efficient core. You can have up to 16 cores here, 8 performance and 8 efficient. You can have a lot of these threads. And Intel has actually developed this thread director that kind of looks at what is going on inside each of these cores and brings this information to the operating system, in this case Windows 11, for Windows 11 to kind of do the scheduling. So the kind of things that I was talking about earlier, which has now become kind of standardized in mobile platforms. When we started doing research in that, there was very little work, but now it has kind of become standardized. And that same thing has to happen again in the server space, and it would be a very, very interesting area to work on. And of course, there is a lot of heterogeneity. For example, with AMD APU, you can see the CPU, the GPU, as well as a lot of other accelerators that are coming into play. And I think it's a very exciting time at this point in time, because again, there is a lot of development that is going on the software space. For example, with one API, you can have a cross-industry open standard-based unified programming model that can run on CPU, GPU, FPGAs, and other accelerators. However, while that was provided, again, in terms of this is built on OpenCL, and OpenCL was providing that for the mobile platform. But I hope I kind of convinced you that that's not just sufficient, because you still need a lot of decisions to make in order to create optimized code for these different systems. You need to decide exactly which ones to use, how to orchestrate across executions, how to remain within the power budget, and so on and so forth. So all these problems that I talked about in the context of mobile systems and a single chip, they are now going to kind of come to the desktop laptop server systems, single chip to chiplets to multi-socket to data centers. And what is however very interesting is that, so these are very complex systems. These are much more complex software, not so well behaved as we saw in case of embedded systems. So this would be a very, very rich and interesting sort of research, as well as development domain where one could work on. And we now have more interesting tools at hand as well. So for example, we can bring in machine learning and AI in order to solve some of these problems. Just like we need to kind of be able to run machine learning workloads on these things, we can actually use machine learning as a tool in order to solve some of these problems. So this is going to be a very, very interesting space to look out for. And the other parallel, which is something that we are doing in my group, is that try to move away from all these domain specific accelerators that are there, which makes the software development really, really complex. So the holy grail of these things is that can we move from domain specific accelerators to a domain agnostic accelerator, which is kind of an universal accelerator that should provide an ASIC like efficiency, but at the same time, it should be programmable through software. Now, that's a very, very difficult goal to achieve, but there are a lot of research that's going on in this direction, in particular in US with the DARPA software-defined hardware program. We are doing something similar here in Singapore in my group, where we are using what is known as coarse-grained reconfigurable array, which is kind of a coarse-grained version of FPGA, if you think about it in a very coarse sense, where we try to create an architecture that's really, really simple, but that's very, very parallel. So simple because it gives low power, parallel because you need to get the high performance, and everything is done via software. So the software compiler kind of maps this onto the hardware, and the hardware just follows those instructions. So this can actually lead to significant power efficiency, especially in the context of IoT systems and mobile platforms. And as with anything today, you cannot just define the hardware, you cannot just define the compiler, you need to go all the way up from the application side all the way to the end. So I think this is a very interesting time. The heterogeneous computing systems gives you a trade-off between performance, power, and predictability. I hope we get to see a lot of advanced development in this domain going forward. I would like to thank all my collaborators this is Marina Bay Sands in Singapore. You can think of it as homogeneous computing, very, very nicely done. This is kind of the mess that we are in at this point in time in terms of heterogeneous computing, and hopefully we can go to this kind of a nice design where finally everything falls into place. So with that, thank you very much, and I'm happy to take questions.
Yeah, thanks, Tulika. There's one question on the chat window. I have a few questions as well, but let's take the question on the chat window. It reads a lot of great content. So thanks for that, Professor Mitra. And the question is, how can these techniques and analysis apply to heterogeneous integration, where the engine is split into several discrete identical chips for better yield, but combined on a high density substrate? What would be the difference?
Yeah, no, thank you. Thanks, Paul, for that great question. And as I mentioned, that we have looked at it in the embedded systems context on SoC, but AMD, for example, it's a chiplet-based design where you are going to look at, all these things across the chips. I think the theoretical part of it, or the fundamental part of the concepts remain identical. What becomes more challenging is the overheads that will happen in order for you to kind of transfer the data across these chiplets. That's much more compared to what you are seeing here, and that actually makes a huge difference. What we saw in kind of machine learning workload is that if I take a kernel and I try to split it across, for example, even the two clusters, the big clusters and the small cluster on the same chip, there was so much overhead that it didn't make sense. So you had to put things into one cluster and minimize that communication. So I think as we go for kind of multi-chip solutions, that overhead of communication is the one that's going to play the bigger role in our mind, and which is something that we need to model much more than what we are doing right now.
So it's the supervision and control that get to be the issue as you split the chips.
Sorry, can you repeat that?
Yes, it's the supervision and control issues that cause the problems when you split the chips, as opposed to having a single SoC that you can control, you understand better.
That's correct. That's absolutely.
Thank you.
Thank you.
So it wasn't very clear from the presentation, or maybe I missed it. So did you say that the RTL generator is responsible for distributing the workload to the various chips?
No. The RTL generator is responsible for creating the code for, so for example, if you have an FPGA, then what the way you do it is that our tool will tell you that this should be the pragma choices. This should be the way the loop should be unrolled. This is the number of times, you need to unroll the loop. This is the whether you should use loop pipelining or not, whether you should use array partitioning or not. So these are kind of high level decision making. What should be the tile size? So these are kind of high level decision making that will be provided by our tool, saying that this is the best. Then you have a lot of high level synthesis tools. For example, for Xilinx, you have the Vivado. So that can take in those parameters, that can take in the code, and it can actually generate an RTL code. Okay, so that RTL code then will be placed on the FPGA, but you need a supervisor or a controller of some sort, right? That needs to be able to distribute the workload between the CPU and the FPGA, and that's kind of that can be either a middleware layer, or it can be the operating system that takes care of it. So the software kind of provides hint that this portion should go here, this portion should go here, and then at the end of the day, either the operating system or if you are using OpenCL, for example, as soon as you give that hint, that place that particular piece of functionality will be moved to the appropriate appropriate device, right? So it depends on which kind of system you are in. If you are using an OpenCL platform, then it's fairly straightforward. You just have to tell that this particular function should go here, and this is the corresponding code, RTL code, and that's it, right? For others, like for example, for most FPGAs, it's fairly more complex, and you need kind of in-house sort of operating system to do that distribution. And yeah. Does that kind of answer the question?
Yeah. So so you also seem to have mentioned that machine learning is used for the distribution of the load itself, or you said
yeah. So what we are hoping that this problem gets really, really complex once we go into the server space with lot of complex software. Right now, the way we are doing things is that we have actually access to the source code. So we have C, C++, Python code, and then we are kind of analyzing that code. But you might not have access to that. You might be working with legacy code, the binary software binaries. And in that context, it's kind of a program analysis that requires more information, may or may not be feasible. And the hope is that with kind of a machine learning tools, we would be able to kind of get the features out of these from these binaries, and we should be able to say that, okay, where should it go, and at runtime make the decisions. Because already, I mean, it's happening that you kind of look at what's happening across the system. And Paul was kind of talking about a much more complex system based on chiplets and stuff like that. And then you need to get this information from the different parts, and you make use of that make use of those in a machine learning approach to kind of make the decision, where should this task go? Should I migrate this task? What should be the dynamic voltage and frequency scaling for each of these components? Whether we should shut down some part of the system, and so on and so forth. So the power management and the thermal management, as well as the task scheduling, can potentially move to a more machine learning based way of doing things.
So if that happens, the machine learning model is going to sit inside the operating system, right?
Correct. That's right. Yes. Yeah.
Wow.
So right now we kind of use a control theory based approach, right? Which is which is kind of a reactive response, right? So you look at what's happening and you try to kind of, go towards your goal. We kind of, this is not available in commercial approach, but we try to play around using kind of, a price theory based kind of techniques, borrowing from economics, where you try to kind of make the supply demand kind of, go at the right point, and you can kind of prove that this is an optimal solution. But all of those things require a lot of manual thinking in order for you to come up with the best way of doing things, right? And so if with machine learning we can kind of sort of automate that process and let a small module be sitting inside the operating system to do this, that would be a great thing, I think.
So this distribution, I don't see any other questions, so I'll probably use this opportunity to ask another question. So the distribution of the workload, right? Again, going back to that question. So that requires the operating system to actually know make decisions at the instruction level, right? Given a binary executable.
No, not at the instruction level. It's more at the sort of what we call the loop level. So, so if you look at any piece of code, what you can accelerate are really the compute intensive loops or the loop nest, so to say. You try to map those loop nests to the different compute elements, be it FPGA, be it GPU, and so on. And the rest of that part, you should leave it on the CPU, because you are not going to get any benefit by moving them onto any accelerator whatsoever. And then those kind of single execution, there is no loop, they do not work well on any other accelerator. So so what happens is that the code comes in, and at each sort of loop nest there is a kind of a hint, right, that this can be sent to sent as a thread on the GPU, or it can be sent as a thread on the FPGA, right? Sometimes you can be very specific and you can say that, okay, this thread should be spawned on the GPU, or this thread should be spawned on the, I mean, I'm kind of using the term thread. It may or may not have a thread concept, but essentially, that where you should send it. And if you have made already that decision statically, then that's well and good. If you have not made that decision, then you might actually give some hint along with the code that says that, this is going to be the performance of this particular loop nest on these different platforms. And the operating system can look at what is available right now and make a choice in terms of, what is available, what is best for this, right? And kind of make that dynamic decision. That's not what we are doing right now. We kind of statically decide everything. And we say that this is the type of code that it should go to. Operating system can, of course, choose from multiple instances of that type, but the type is defined by us. But moving forward, one can imagine that even the type can be like, if you go on an FPGA, it's going to be 1.5x improvement. If you go on a GPU, it's going to be 3x improvement. But maybe your GPU is already heavily loaded with, applications that are best for that. So maybe, you take your second choice, which is the GPU. Does that make sense?
Yeah, definitely. So any other questions from anyone? So I think this will be a great boost to edge computing, right?
That's right. Yes. So this has come from the edge computing space, and the reason that it is because we have been very limited by power, right? And yet we need that performance. So yeah, so this is all in the context of a really edge computing space, and you can see all the things that have happened in the mobile. is moving to the edge at this point in time, right? The same chips you are seeing that, they are making appearance in UAVs, for example, or even like, my smartwatch or smart glass and things like that. So that would be a very, exciting space to look at.
And what are some of the research areas in this field, in this
edge
topic? Yeah.
So for edge computing, the most important point at this point in time, I think, is that it has become a lot of machine learning code, in a lot of sense. The lot of work is going on in kind of having the edge AI accelerators. I think that's the hottest sort of domain at this point in time. How do you really sort of, instead of sending the data to the cloud, can you actually get things done at the edge itself? And there are a lot of benefits for that. First is, of course, the privacy reasons and so on and so forth. You might not want to send the data. But second, and most importantly, this is important for sustainability, as in, sending the data across to the cloud is very, very expensive in terms of energy. You are much better off doing things at the edge itself. And the third most important point is that right now we generate a lot of data, but we use 10% of the data from the edge. 90% of the data is just wasted, thrown away, because there is no way for us to send it to the cloud and do the processing. So we want to kind of make sense of the data at the edge as much as possible without going to the cloud. I think that would kind of reduce the carbon emission of the ICT industry by almost half, if we can actually manage to do that, and also kind of able to support a lot of sort of real-time computing needs. A lot of applications, in particular, if you're looking at automotive, factory automation and things like that, a lot of this is real-time. You cannot afford to send this data across. So how to do all that processing at the edge without going to the cloud is something that's the most, I think, most challenging part at this point in time. It's also a very, very fragmented industry, right? Unlike server space, you have a lot of players there, and I think again, a lot of hardware development is going on, which is great. But how to support that in terms of software is, again, another very difficult challenge that we are facing, in particular for what has become now known as TinyML, which is kind of being able to support machine learning on MCU or microcontrollers, right? And so that's, again, a very, I think, exciting space where a lot of research is going to is happening and going to happen in the near future.
So I think this workload distribution, using machine learning for workload distribution, would also come in that space, like TinyML?
Not so much. I do not think so, because for TinyML, you have so little area that you cannot afford to have so many heterogeneous compute elements there. Instead, what you probably want to have is just one or two, probably just an ML accelerator or an FPGA, or we are trying to push for coarse-grained reconfigurable arrays, and then you have the CPU and maybe a GPU. So that kind of very complex sort of workload distribution is probably more going to happen in the server space, or the laptops, or that kind of a little bit bigger. I can even imagine that it's happening on my mobile phone, but I cannot imagine that's happening in a TinyML device, because we need to be really cognizant that every milliwatt counts there. So you can only have very simple sort of strategies out there, mostly done at statically, and then runtime, very little decision making.
So any other questions from anyone?
No, I think we can probably wrap it up. What do you think, Vishnu?
Yeah, we can. I just wanted to make announcement for the next talk, IEEE talk, and then so thank you, Professor Mitra. It was really very insightful and a lot of content, like our audience also has acknowledged. It was really very insightful, and really appreciate you taking time to talk to all of us. So our next event, so I don't know if I'm sharing or, okay, I think I'm sharing. So our next event is the Ask Me Anything session with Professor Pedro Domingos. He's a renowned expert in machine learning areas from University of Washington. So that's on the 9th of November. But we are expecting the questions to be sent in advance. Of course, the audience will, of course, get a chance to ask questions during the session as well, follow-up questions. But the primary questions, if they can be sent to us in a week, that would be great. So the events are all listed on our website. Please feel free to check our website, and hopefully all of you are going to attend this talk as well and make it a success, just like this talk. With that, I once again thank Professor Mitra, and hope we'll be able to invite you again sometime in the future. Thank you.
Thanks
Thank you,
very much.
everyone, for attending.
Mhm.
Sorry, you were saying something, Paul?
I was going to say, I should have this edited in about a week. I'll pare it down and get rid of any bloopers, and we'll have it on our website. We'll send an email out to the Eventbrite registrants at that point with the link.
Yeah, sounds good.
Thanks, everybody.